Good morning, everyone. Today we are going to start solving problems related to Chapter 1 in molecular physics. I will start with this problem. Calculate the frequency mu in hertz and the wave number mu bar or nu tilde in centimeter minus 1 for the following wavelengths. So he has given me 3 lambdas, 10 centimeter, 10 micrometer, and 300 millimeter, and he's asking me to find the frequency and the wave number. Before finding the frequency and the wave number, let's revise the characteristics of a wave. What is the frequency? So, characteristics of a wave. Characteristics of a wave. So first, the frequency, given usually the symbol nu if we are talking about a light wave or an electromagnetic wave. So what is the frequency nu? It is the cycles performed per unit time. So that's why nu has the formula 1 over t لأنه هي بتعمل cycle واحدة بperiod واحدة. Recall that t is the period. It is the time needed to perform one cycle. Because t is the time needed to perform one cycle, it is time, so its SI unit is seconds. If t is expressed in seconds, then nu will be expressed in hertz, which is the SI unit of frequency. Now let's talk about the wavelength. The wavelength is given the symbol lambda. What is the wavelength? It is the distance traveled during one period. The distance, it's not a time. Distance traveled during one period in one cycle. So distance traveled in one period. So lambda has the unit, SI unit, meter. It can be expressed in other units as here. It can be expressed in centimeter, micrometer, millimeter, and unit related to distance, but the SI unit is meters. Besides, the wave has a speed. Why the wave has a speed? Because it's moving through space through a certain time, so it must have a speed. What is the speed of a wave? Speed v. It's equal to the distance traveled over the time traveled, or simply the distance traveled in one cycle, which is lambda, over t, the period. ليش؟ لأنه هي بتقطع مسافة لامدا خلال الوقت t. So السرعة هي distance over time, it's simply lambda over t, or it can be expressed as lambda times nu. If we are talking about light wave or an electromagnetic wave, which is moving in vacuum or air, for sure V will be equal to C. So in vacuum or air, so V is equal to C, then we will get C equals lambda nu. So like this. This is a relation between C lambda and nu, and you can clearly see that nu, the frequency, is equal to C over lambda. So if we have lambda, we are able to, this is the first formula, if we have lambda, we are able to calculate nu. So if C is expressed in meters per second, which is the speed of light in vacuum, lambda must be expressed for sure in meters so that meter and meter cancel, and we remain up with 1 over seconds, which is hertz. So we will get the frequency in a unit of hertz. Okay. So you all know that C is equal to 3 times 10 to the power 8 meter per second. This is a constant, the speed of light or an electromagnetic wave in vacuum. So now we are able to calculate nu easily, given lambda for the 3 parts. We just substitute in the equation and we get nu. Now what is the wave number? We did not speak yet about the wave number. The wave number, let me write it down. So now the wave number is the spatial frequency related to spatial frequency. You will see how. So it's the spatial frequency of a wave. In other words, it is measured in cycles per unit distance. Let's compare the wave number with the frequency. The frequency is the cycles per unit time, while the wave number is the cycles per unit distance. So they are similar. يعني الفريكونسي كم سايكل بيعمل باليونت تايم الوحدة بالثانية، بينما الويف نمبر كم سايكل بيعمل بالمتر بالديستنس. So it's somehow frequency بس بلا frequency على الوقت، كم سايكل بيعمل بالثانية، كم يعني إذا هو قطع متر كم سايكل بيكون عامل فيهم. هونيك لا، بالثانية الوحدة بالوقت الواحد كم سايكل بيكون عامل. So this is the difference between a wave number and the frequency. Usually there are two types of wave numbers. Ordinary wave number, so here I'm talking about the ordinary wave number. Ordinary wave number. So it's given usually the symbol nu bar, nu tilde. It can be written as I've written it up. So this one is equal to 1 over lambda. Why do we give it this formula 1 over lambda? لأنه بيعمل سايكل وحدة خلال مسافة لامدا. So I divide the number of cycles over the distance traveled. I get the ratio number of cycles per unit distance. مثل فوق بيعمل سايكل وحدة خلال وقت t. هون بيعمل سايكل وحدة خلال مسافة لامدا. So this is the difference between the frequency and the wave number. So as you can see, if we substitute lambda for meter, we will get nu bar or the wave number meter minus 1. So if we substitute lambda in centimeter, we can get nu bar in centimeter minus 1. So it depends on choosing the unit for lambda. All of them are okay. You are okay with all of them. However, m is the SI unit for lambda, which gives m minus 1 is the SI unit for the wave number. This is called the ordinary wave number. In fact, there's another wave number called the angular wave number. So the angular wave number, so it's similar to this one. So the angular wave number is or measures, let me say, radians per unit distance. يعني كم radian بيعمل بال1 meter. So this is giving usually the symbol K. K is equal. نحن بنعرف خلال سايكل وحدة بيكون عمل 2 باي radians وقطع مسافة لامدا. So the formula for K is 2 pi over lambda. Up we have the unit radians, down we have the unit meter, so K for sure will be in radians per meter. So the difference between the wave number and the angular wave number is simple. So it's either number of cycles, يعني كم cycle عمل بالمتر الواحد, this is wave number. كم radian عمل بالمتر الواحد, this is the angular wave number. Simply nu bar it's 1 over lambda, K is equal to 2 pi over lambda. We're going to concentrate on the wave number, the ordinary wave number, and not on the angular wave number. However, the angular wave number also appears in other lectures, and you see it for sure. So let's mark this in red. This is our formula for the wave number. For sure, there's a relation between nu and nu bar, the normal frequency and the wave number. The relation is very obvious. It's that. So nu equals c over lambda, and nu bar equals 1 over lambda, which gives that nu equals c nu bar. If we have nu, you can calculate nu bar, or vice versa. Now let's move back to our question. In our question, he gave us lambda equals 10 centimeter, and he's asking us to calculate nu and nu bar, or the wave number and the frequency. So let's start. A. You can calculate any one before the other. So let's calculate nu equals c over lambda. For example, this is the frequency. Nu is equal to 3 times 10 to the power 8. This is expressed in meter per second, so I have to change lambda to meters. Lambda was given to be 10 centimeters, so I will put it as 0.1 meter. Dividing these two, we will get 3 times 10 to the power 9 hertz. So this is if I'm going to calculate nu. Now how to calculate nu bar? You can either use the formula 1 over lambda or the formula nu over c. Both of them are correct. So 1 over lambda will give me. But just going back to the question, I can note that he was asking me to find the wave number in centimeter minus 1 and not in meter minus 1. So I have to pay attention either to change it from the beginning or to change it at the end. So if I substitute lambda in centimeters, I will get a nu bar in centimeter minus 1. So I will keep lambda in centimeter, it's 10 centimeter. So I will get 0.1 centimeter minus 1. Can I get nu bar out of nu? Yes, we can do that. Or let's do a second method. Nu bar is equal to nu over c. It's equal to 3 times 10 to the power 9 over 3 times 10 to the power 8, which is equal to 10. Because I have used SI units here, this is expressed in hertz and this is expressed in meter per second, I will end up with a unit of a meter minus 1. Now, how to change from meter minus 1 to centimeter minus 1? So things are simple. Just imagine m minus 1 is simply 1 over m. So it's 10 over 1 meter. So it's equal to 10. If I'm going to change meter to centimeter, I have to multiply by 10 to the power 2 centimeter, and I will end up with 0.1 centimeter minus 1. So you can see that to move from meter minus 1 to centimeter minus 1, I have to divide by 10. I have to divide by 10 to the power 2, 10 squared, or I can multiply. Let me write it as a multiplication. So I can multiply by 10 to the power minus 2. So this is our trick. To change from centimeter minus 1 to meter minus 1, it's the opposite, so we'll multiply by 10 to the power 2. So that's clear. Now let's do the second part. I will do the second part, you'll do the third part on your own. In the second part, we have lambda, it's equal to 10 micrometer. So B, lambda equals 10 micrometer. So you all know that 10 micrometer is equal to 10 times 10 to the power minus 6 meter. Let's change and calculate the wave number before the frequency. So nu bar equals 1 over lambda. Let's substitute lambda in meters, it's okay. So 10 times 10 to the power minus 6, which is 1 over 10 to the power minus 5. This is in meters, which will give us 10 to the power 5 meter minus 1. But he was asking us to give it in centimeter minus 1, so we simply just multiply. by 10 to the power minus 2, so 10 to the power 5 times 10 to the power minus 2 centimeter minus 1, we will get 10 to the power 3 centimeter minus 1. So now let's calculate nu, the frequency. You can use either nu equals c nu bar, or you can use the formula nu equals c over lambda. So I will use the easier one, which is nu equals c nu bar. It's equal to 3 times 10 to the power 8. So this is in meter per second. So I have to substitute nu bar in SI unit, which is 10 to the power 5, so that meter will be cancelled with meter minus 1. So we will get 3 times 10 to the power 8 plus 5, it's 13 hertz. If someone wants to use the basic formula, nu equals c over lambda, it will give the same answer, times 10 to the power 8 over, this is in meter per second, over lambda in SI unit, it's 10 times 10 to the power minus 6 meter. This will give us 3 times 10 to the power 8 over 10 to the power minus 5, and it's the same 3 times 10 to the power 13 hertz. You can see that both methods. For the last part, lambda is given to be, this one must be nanometer, so it's 300 nanometer. So I'll give you the answers, you can do it on your own. So this is lambda equals 300 nanometer, which is equal to 300 times 10 to the power minus 9 meter. Now I have already calculated the wave number. It's equal to 0.333 times 10 to the power 7 meter minus 1, which is equal to 0.333 times 10 to the power 7 times 10 to the power minus 2 centimeter minus 1, which is written as 0.333 times 10 to the power 5 centimeter minus 1. Nu was found to be 10 to the power 15 hertz. You can do them on your own. Now let's move to the second problem. On an infrared spectrum, we observe a peak at a wave number 1686 cm minus 1 due to the absorption of carbonyl group. The value for the transmission is read on the spectrum to be 4%. Find the value of the absorbance. So he said that the transmission is 4% of the spectrum. So we can deduce that T equals 4%, which is equal to 0.04. And he's asking me to find the absorbance, A. So what's the relation between T and A? The relation is quite simple. A equals minus log T. And I have already explained this in the lecture. So it's minus log of base 10 for sure, 0.04. So using your calculator, you will get 1.397, which is approximately 1.4 unit absorbance. So this is for this problem. This problem says, on a UV visible spectrum, we observe a band that has a maximum found at the wavelength lambda equals 340 nanometer. The value of the absorbance measured at this maximum is 0.55 unit absorbance. So this is the absorbance A. Find the value of the transmission factor. So we're going to find T. Here he gave us A and he's asking for T. So let's do that. A is equal to 0.55, and we have figured out in the previous problem that A equals minus log T. It can be written as minus A equals log T, which is 10 to the power minus A equals 10 log T equals T, and we arrive to the formula T equals 10 to the power minus A. So if we have A, we can find T, and if we have T, we can find A. So let's use this formula. T equals 10 to the power minus A equals 10 minus 0.55. Using your calculators, you can find out it's equal to 0.28. If we want to write it as a percentage, we multiply it by 100, it will be 28%. A solar protection cream is based on the absorption of ultraviolet radiation by titanium oxide particles. For an aqueous solution with a concentration of 1 mg per liter, we find the absorbance to be 0.3 at 180 nanometer when the width of the container is 1 centimeter. So he's giving me the absorption at a certain wavelength and the width of the container, and for sure the concentration of the solution. What should be the concentration of the particles in milligram per liter in a film of this solar cream of thickness 0.3 mm if the film absorbs at least 90% of the ultraviolet radiation at this wavelength? So this lacks a T. Let's understand the problem. We have a solution of solar protection cream. This solution contains particles called titanium oxide particles. These particles are responsible for absorbing the ultraviolet radiation. So what did he give us? He gave us some characteristics for this solution. For a solution that has a concentration C equals 1 milligram per liter, this solution has an absorbance A equals 0.3 at a wavelength lambda equals 180 nanometer. For a container of width L, so if the solution is placed in a container that has a width L equals 1 centimeter. So he's asking me about the same particles but with different situations. What should be the concentration? So same particles, which are titanium oxide particles, what should be their concentration? We have to find their concentration. If they were found in a film with new thickness, which is L prime, equals 0.3 millimeter, and he gave us that the film absorbs 90% of the ultraviolet radiation, he means that the absorption A is equal to 90% or 0.9 at, for sure, lambda equals 180 nanometer. Out of this absorption, we're able to calculate the transmission. So for sure, if the absorption is 0.9, the transmission will be simply 0.1. And we can calculate the absorbance A prime, which is equal to minus log T, and it will be equal minus log 10 to the power minus 1, it will be 1. So you can see that the particles are the same in both cases, but concentration, the absorbance, the width are different. What's common between both? The particles. So which means that in both cases we have the same molar absorption coefficient, same epsilon. So if we calculate epsilon in the first case, it can be substituted in the second case. Epsilon is a characteristic for the particle. يعني قد ايه عندها البارتيكل قدرة تمتص مرتبطة بالبارتيكل. Okay, so for the same particles, it's at a certain wavelength, it's the same. It doesn't change. حتى لو أنا غيرت السوليوشن وغيرت الشيب, الكونسنتريشن إلى آخره. So let's do that. Let's use Beer-Lambert law, and after that find epsilon from the first case and try to insert it in the second case and then find C prime. So using Beer-Lambert law, we have A equals epsilon L times C, which gives that epsilon equals A over LC. Let's substitute. A is equal to 0.3, it's unitless. L, it can be kept in centimeter, which is the unit usually used. And C is in milligram, so it's 1, this is centimeter, this is 1 milligram per liter. So we will end up with 0.3 liter milligram minus 1 centimeter minus 1. Now let's use this epsilon to find the concentration in the second case. So same formula, Beer-Lambert law for the second case. We will get, so now C prime equals A prime over epsilon L prime. Epsilon remains the same particle, same epsilon. Equals, A prime is 1, it's unitless. Epsilon is 0.3 L liter, milligram minus 1, centimeter minus 1. L prime, it was given in millimeter, it's 0.3 millimeter, so I will change it to centimeter, so that centimeter with centimeter minus 1 cancel out. So it's 0.3 times 10 to the power minus 1 centimeter. So this is cancelled with this, and we will end having an answer of 111 milligram per liter. And this is the final answer. This question says, write the expression for Beer-Lambert law, precise the unit of each physico-chemical parameter in this expression. So we all know the answer of this problem. This is just a revising problem. So A, the absorbance equals epsilon LC. This is Beer-Lambert law, and the absorbance has a unit of unit absorbance, or it's unitless. The concentration has a unit, usually mole per liter. The distance or the thickness has a unit of centimeter, which gives the molar absorption coefficient a unit of liter centimeter minus 1 mole minus 1. So how to apply this law when the sample contains multiple absorbing substances? What to do if we have multiple absorbing substances? We have also spoke about that. So we just write the absorbance as summation of different absorbances corresponding to different particles inside the substance, which gives us L, which is the width of the container, multiplied for sure by the summation over I, epsilon I, C I, for sure for a certain wavelength lambda. So for each absorbing substance, so I is the summation of different absorbing substances or different absorbing molecules. So if we have 2 types of molecules, 3, 4, etc., so we do a summation. Epsilon I is the molar absorption coefficient for a certain substance, and Ci is its concentration, and so on. So now for this one, let's move to the last one. We need to determine the concentration in mole per liter of 2 salts, A and B, in an unknown sample in aqueous solution. So we have to find the concentrations of A and the concentration of B. We record the spectrum in the visible range for each of these salts measured separately in aqueous solution, as well as for the sample solution to be analyzed. The optical path for the containers used is L equals 1 cm. The values of the measured absorbance at 510 nanometer and 575 nanometer for the 3 measured spectra are. So we measured A alone, at two wavelengths. We measured B alone at two wavelengths, and then we mixed them up with certain concentrations, and we're going to find these concentrations using the properties that we have studied. So for salt A, with a concentration 1.5 times 10 to the power minus 1 mole per liter, we have found that the absorbance was 0.714 at 510 nanometer and 0.097 at 575 nanometer. For salt B, for a given concentration, we have done our experiments and we found that the absorbance at 510 nanometer is 0.298 and at 575 nanometer it is 0.757. Now the sample solution that we are studying, which is a mixture between A and B, showed that it has an absorbance of 0.4 at 510 nanometer and 0.577 at 575 nanometer. So this absorbance is due to both salts A and B. We have to find the concentration of A and the concentration of B in this sample solution. In the first part, it says calculate the 4 molar absorption coefficient for salt A at 510, for salt A at 575, for salt B at 510, and for salt B at 575. So for each salt separately at a certain wave. Remember that molar absorption coefficient for a certain salt or for a certain particle is a characteristic at a certain wavelength. يعني بيبقى المولر absorption coefficient هو ذاته لهيدي الموليكول أو لهيدا السولت على هيدي الويفلينث وين ما كان هيدا السولت أو هيدي الموليكول موجودة. Okay, so we can use these molar absorption coefficients when we find them to deduce later the concentrations of A and B in the sample solution. So let's first start finding epsilon A at 510. So this is part A. Using for sure Beer-Lambert law. So for lambda equals 510 nanometer, we have A, which is the absorbance for salt A at 510, is equal epsilon of A at 510, concentration of A times the width of the container. Remember, we are trying to find epsilon, which gives us epsilon of A at 510 equals absorbance over L, concentration of A. We have everything. We have the absorbance. Where is it? Here it is. This is the absorbance. It's 0.714. The width is 1 centimeter. And the concentration, here it is, it's given. It's 1.5 times 10 to the power minus 1 mole per liter, which gives us an answer of 4.76 liter centimeter minus 1 mole minus 1. Let me write it down. Mole per liter, which is equal to 4.76 liter centimeter minus 1 mole minus 1. Similarly, we can calculate epsilon A 575. So epsilon A 575 equals the absorbance at this wavelength over the width of the container times the concentration of A. Where's the absorbance? Let me write this. Where's the absorbance? Here it is. It's equal to 0.0097 divided by 1 centimeter times 1.5 times 10 power minus 1 mole per liter, and we will arrive to our answer, which is 0.0646 liter centimeter minus 1 mole minus 1. Or we can say it's approximately 0.065 liter centimeter minus 1 mole minus 1. Let's do the same for salt B. So epsilon B at 510 equals the absorbance over L concentration of B. From the given, you can see that the concentration of B is 6 times 10 to the power minus 2, and the absorbance at 510 is 2.298. So it's 0.298 over 1 centimeter, 6 times 10 to the power minus 2 mole per liter, and we will arrive to the final answer, which is 4.966 liter centimeter minus 1 mole minus 1. The last one is the molar absorption coefficient at 575 for salt B. 575 is equal to A over L concentration of B. A is how much? Let's look at the given. Again, it's 0.757 divided by L is 1 centimeter. It's the same for all cases. It was given in the problem. CB is the concentration, same as here, 6 times 10 to the power minus 2 mole per liter. We will end up with a final answer of 12.6 liter centimeter minus 1 mole minus 1. Now let's move to the second part. In part B, give the expressions, formulas of the molar concentrations for the two salts A and B in the sample solution as a function of the molar absorption coefficients, the length of the optical path, and the measured absorbance of the mixtures. Calculate these concentrations. For the sample solution, we have as a given an absorbance of 0.4 at 510 and an absorbance of 577 at 575. So let's write the given and try to find the concentration of A in the solution and the concentration of B in the same solution. So this is part B. A of the solution at 510 was given to be 0.4, and the absorbance of the solution at 575 was equal to 0.577. This is the given. We're going to find the concentration of A in the solution and the concentration of B in the same solution. We have two unknowns. We have to search for two formulas. We have to make benefit from the previous part. The solution contains two salts, A and B. So its absorbance is the sum of the absorbance of the first salt plus the absorbance of the second salt. So we can write it like this. So the absorbance of the solution at a wavelength of 510 is equal to L times the summation over I. I runs over the salts in the solution, A and B. Epsilon I Ci, which means simply L into the molar absorption coefficient of A, the concentration of A that you are looking for in the solution, for sure, and the molar absorption coefficient of B times the concentration of B in the solution for sure. Okay, so these molar absorption coefficients are at 510 nanometer. They are the same as those calculated above because they are characteristic of the particles of the salts, did not change. Even if I do a mixture epsilon for salt A، يعني قديش عنده ال A القدرة إنه هو يمتص، رح تبقى هي ذاتها على 510. بس توتال مع بعض ال A وال B عم يطلع أنا معي absorbance جديد. بس كل واحد لحال عنده molar absorption coefficient هو بيسمى molar absorption coefficient. كمية الابسوربشن كلها بتعتمد على كمية البارتكلز، بينما المولر absorption coefficient هو عبارة إذا بدكم بيشبه الدنسيتي، ما بيتغير. Okay, it always remains the same. It only depends on the salt and on the used wavelength. So this is the first equation. You can see clearly that we have everything ما عدا CA و CB بقلب السوليوشن. يعني concentration of salt A and salt B inside the solution. So we need another equation to finish this thing up and to find CA and CB. First, let's substitute here and create an equation. So we have this 0.4. It has no unit. L has a unit of centimeter. It's 1 centimeter. It is the same. Epsilon A, we have found it up. هيا هون تطلع 4.76 concentration of A in the solution plus the second one, the concentration of B at 510, it is 4.966 concentration of B in the solution. Okay, so we have everything. You can multiply them or just keep them like this. It's okay. So now let's do a second equation. This is equation 1. The second equation is using the absorbance at 575 for the solution. It has the same formula as the summation over the two salts, epsilon I, Ci, which means it's L epsilon of A at 575 concentration of A in the solution plus epsilon B 575 Cb in the solution. Similarly, we have everything except Ca and Cb. So we will get 0.577 equals 1 centimeter, and this was found to be 0.065 Ca in the solution plus 12.6 Cb in the solution. This is equation 2. So 1 multiply 1 by it's the same. So we have two equations, two unknowns. Use your calculator to solve them. No need to do an effort. You just can use your calculator, enter the coefficients, and you will find the answers. So solve 1 and 2. Then we will get Ca, try it at home, it will be 0.036 mole per liter, and Cb will be 0.0456 mole per liter. And that's it.